Welcome back. Now we will go over section 2.7, graphing techniques. Reflecting across an axis, the graph of y is equal to the opposite of f of x is the same as the graph of y equals f of x, reflected across the x-axis. If a point xy lies on the graph of y equals f of x, then the point x comma minus y lies on this reflection. So if you notice, what we did was we took y and made it the opposite. When we reflect across the x-axis, the y values become the opposites of what they originally were, and the x-axis doesn't change. The x values don't change. Next, the graph of y equals f of the opposite of x is the same as the graph of y equals f of x, except for it's reflected across the y-axis. It says if a point xy lies on the graph of y equals f of x, then the opposite of xy lies on this reflection. In other words, the x values become the opposites of what they were, and the y values remain the same. So let's look at some functions. We're going to start off with our parent function. F of x is equal to the square root of x. It's drawn here. Excuse me. Next, we want to say compare that to g of x is equal to the opposite of x. That's that top set of information I gave you. The graph of y equals the opposite of x. It says the y values would change. So look at this. This is the function g of x. The x values are the same, but the y values are the exact opposites of what they were. The last one is h of x in purple. H of x is equal to the square root of the opposite of x. That says I'm going to take all my x values and change their values to be the opposite of what they were, but the y values will remain the same. So this is how we discuss reflecting across an axis. Please remember these rules. If I'm reflecting across the x-axis, the y values become the opposite, because you will need to do this on your test. I will give you points and you're going to figure out how to reflect them. And that's also how we're going to move things when we start doing translations. Also remembering that if I'm going to reflect across the y-axis, the x values become the opposites of whatever they were, and the y values will remain. Symmetry. Symmetry, remind me, is that whole concept of having almost like a mirror. It says symmetry with respect to an axis. The graph of an equation is symmetric with respect to the y-axis if the replacement of x with the opposite of x results in an equivalent equation. So if I replace the x with a minus x and once I process that value, if the result is the exact same equation, then it is symmetric with respect to the y-axis. Next, we want to talk about the graph of an equation is symmetric with respect to the x-axis. Since the replacement of y with the minus y results in an equivalent equation. So if I replace y with the opposite of y and I process it, and I have the exact same equation, then it is symmetric with respect to the x-axis. So we're going to consider symmetry with respect to an axis. So let's test for y-axis first. That means I'm going to replace x with the opposite of x. So y is equal to the opposite of x. I'm going to square it plus 4. Y equals, when I square the opposite of x, that becomes positive x squared plus 4. That's the original equation. So we would say that is symmetric with respect, WRT, to the x-axis. Because this equation and this equation are the same after the replacement of x with the opposite of x. If it's respect to the x-axis, the y-axis, then we don't need to check the other. So now let's check it again. A different equation. We're going to look at y squared minus 3 is equal to x. We're going to first check with the y-axis. So let's test for the y-axis. Again, that means replacing x with the opposite of x. So I have y squared minus 3 is equal to the opposite of x. When I process that one, that doesn't quite look the same. It's not the same, so not symmetric with respect to the x-axis, to the y-axis. I just noticed I had written up here x-axis and it was y-axis up there, because that's what we were testing for in the previous problem. So I've tested problem B for the y-axis. Now I'm going to test it for the x-axis and see if it would, maybe it will pass that one. So let's test for x-axis. And again, according to the definition up here, it says I'm going to replace y with the opposite of y. Here's a quick reminder. If I'm testing for x-axis, I replace y with opposite of y. If I'm testing the y-axis, I replace x with the opposite of x. So if it's whatever that axis is, it's the opposite variable that I'm replacing. So we're going to replace y with the opposite of y. Minus 3 is equal to x. When I take the minus y and I square that quantity, I get y squared minus 3 equals x. Well, those two equations are the same. So it is symmetric with respect to the x-axis. So we've proven that this one's symmetric with respect to the x. Now let's look at C. Again, first, let's try to see if it's symmetric with respect to the y-axis. Let's test for y-axis. That again means replace x with minus x. So it's 2 to the minus x plus y is equal to 4. 2 times the minus x is minus 2x plus y equals 4. That does not get me back to the original equation. Therefore, it's not symmetric with respect to the y-axis. Let's try the x-axis. And again, that says replace y with the opposite of y. So I have 2x plus a minus y is equal to 4. 2x minus y equals 4. It does not look like it's the same equation, so therefore it's not symmetric with respect to the x-axis. So it's not symmetric with either x or the y-axis. Here's another thing we want to look at. We've looked at the x-axis and we looked at the y-axis, but we haven't looked at something to see if it's symmetric with respect to the origin. And we have a test for that. This problem says the graph of an equation is symmetric with respect to the origin if the replacement of both x and with a minus x and y with a minus y at the same time result in an equivalent. So what we want to do is replace the x with the opposite of x and the y with the opposite of y at the exact same time, process everything, and see if we can make them equivalent to each other. So, test for origin. We're going to replace y with the opposite of y. And x with the opposite of x. I get minus y is equal to minus 2 times, well, that's a negative x cubed, which gives me minus y is equal to 2x cubed. That's not the same, but let's do this. Multiply by negative 1. I do that, negative y becomes y, 2x cubed becomes minus 2x cubed, and now I've processed the whole thing, and I got the same. So we would say it is symmetric with respect to the origin. And again, that test is done by replacing the x with the opposite of x and y with the opposite of y. Let's look at this. Y is equal to minus 2x squared. We're going to check for the origin. We got minus y is equal to minus 2 times a minus x squared. That gives me minus y is equal to minus 2 negative x squared. When I process this, positive x squared. If I multiply 3 by a negative 1, I get y, great, equals, oh, that's a problem, 2x squared. So it is not, since they're not the same equation, not symmetric with respect to the origin. Pretty interesting. So let's look at something going back up here. I'm going to look at a quick graph. Put a line through here. Graph something. This function here, y is equal to x squared. That is symmetric with respect to the y-axis. If I replace any, right, because if I go y is equal to minus x squared, I get y is equal to x squared. That's good. If I look at this function, what do we have earlier for the x-axis? Oh, y squared minus 3. Y squared minus 3 is equal to x. We proved that, and that's what that function looks like. And look, it's reflected. These points all up here have its counterparts below the x-axis. It looks like the x-axis is a mirror. Here's one other example of a problem to look at. I'm going to sketch this, so it's not going to be perfect. This is y equals x cubed. That one we're going to tell you right now is symmetric with respect to the origin. What's interesting is if I take that function, let's see if I can do that easily. If I take this function and I rotate it 180 degrees, it should look like the original, and it does. Again, rotate it 180 degrees, and they should look the same. With respect to the origin, when I rotate a function 180 degrees, it will look exactly the same. Visually, I want to give you an idea of what to look for. Obviously, we still have to do the test of replacing x with a minus x and y with a minus y. So this y equals minus 2x cubed is just a version of y equals x cubed. Okay, so we've talked about that. Now let's talk about even and odd functions. So the function f is an even function if f minus x equals f of x for all x in the domain of x. It's a graph that is symmetric with respect to the y-axis. So that's nice to know. If I'm talking even, then that's all I have to worry about. Right? An even function is using the symmetric with respect to the y-axis test. Since the function f is an odd function, if f of minus x is equal to the opposite of f of x for all x in the domain of f, and by the way, it's symmetric with respect to the origin. So not only is this symmetric with respect to the origin, it's an odd function. Not only this is symmetric with respect to the y-axis, it's an even function. Okay? So we want to determine whether each function defined is even, odd, or neither. So let's first test for even. So instead of g of x, I'm just going to write y is equal to x to the fifth plus 2x cubed minus 3x, because we said it was the test for even. The test for even is the symmetric with respect to the y-axis, which means we replace all the x values with the opposite of x. So I get y is equal to the opposite of x to the fifth plus 2 times minus x to the cubed minus 3 times minus x. I get y is equal to, when I process that, it's an odd number, it gives me this, the odd number of negative values. Negative x, when I cube that, it gives a minus 2x cubed, good. Negative times negative is positive 3x. My goal is to get this function. And if I multiply everything through by -1, do I get it? So if I multiply through, all right, and by the way, it was this, y equals. Well, I already have y equals, so I would say it's not even. Let's try odd. Well, the test for odd says replace x with minus x and y with a minus y. So I have minus y is equal to, well, we already have the minus x part, right? We already did all that work. So I'm just going to be lazy and copy it down. Let's multiply by -1. When I multiply that by -1, y becomes positive, good. Minus x to the fifth becomes x to the fifth. Minus 2x cubed becomes plus 2x cubed. Plus 3x becomes minus 3x. And I believe that is the original equation. Therefore, it's it's an odd function. By the way, not only is it an odd function, it's symmetric with respect to the origin, correct? Okay, let's look at B. H of x equals 2x squared minus 3. Let's test for even. Even means I replace x with the opposite of x, right? Because it's the test for symmetry with the y-axis. We're going to look at y is equal to 2x squared minus 3. I get y is equal to 2 times a minus x that's going to get squared, subtract 3. Y is equal to 2. When I take minus x and I square it, I get x squared minus 3. And that, my friends, is the original equation. Therefore, it's an even function. And by the way, not only is it an even function, it is symmetric with respect to the y-axis. All right, so that is how we will determine algebraically, which you will be asked to do on the test, whether something's even or odd, or neither. Right? If I would have processed both of these and I would have gotten something, let's make up a quick example because I don't have one. C, we'll say g or f of x is equal to x cubed minus 5. Right? We go we'll test for even, which means change x to the opposite of y. I get y minus x cubed. Y is minus 5. Not the same. Odd. Replace y with a minus y. When I multiply that through by -1, I get y, good, is equal to x cubed plus 5. Well, it was supposed to be a minus 5. This one would be neither or neither. That was just a quick one because I hadn't shown you one like that. Let's now move on to transformations. So, we have types of transformations, vertical and horizontal. I like to tell my students when we do these, a vertical transformation actually makes perfect sense, where a horizontal transformation, I like to say, if you're a comic fan, it's bizarro world. It's the exact opposite of what you would think. So, right now I'm going to give you a lot of definitions. You may need to pause this a little so that you can write down some of this stuff. All right. So transformation, vertical stretching or shrinking of the graph of a function. Suppose that a is greater than 0. If a point x comma y lies on the graph of y equals f of x, then the point x comma ay lies on the point of the graph of y equals a times f of x. So if I tell you 5 times that function, the y values get increased by 5. Vertical translations happen on the outside of the function. Horizontal translations happen inside the function. I'll get more explanation when we get to that. So it says if a is greater than 1, the graph of y equals a f of x is a vertical stretch of the graph of y equals f of x. And in B, it says if a is between 0 and 1, not including 0 and 1, then the graph of y equals a f of x is what we would call a vertical shrinking of the graph of y equals a of x, a of f of x. So here's an example. This is the original function right here in black that I highlighted. And then they're going to say a is greater, so it's going to take the function, and it's going to vertically stretch it, and it points out that the original function had the point xy, and now the new one has x comma ay. Alright? So it stretched it. In the next example, it's showing the original function again in black. Then it's going to graph this new function y is equal to a f of x. But this time the a value is smaller than 1, right? The first one, the a value is larger than 1. This time it's smaller, so it's going to have a vertical shrink when we compare the original y values for that x. So the y values are smaller, so it shrinks it. Here's another example. F of x is equal to the absolute value of x. That's the parent graph. Then we have the function y is equal to g of x. G of x is equal to 2 times the absolute value of x. Now we look, when x is negative 2, I get a 2 in the original, but I get 4, twice the size. Negative 1, when I process that into the original function, I get 1. But with 2 times the absolute value, the y values are twice as large. 0, well, I can't make twice as large as 0 because it's just 0. When I put 1 in, I get a 1 for the result. But 2 times the absolute value of x gives me twice the value, or 2x. When I look at x equals 2, and I process in the function f of x is equal to the absolute value of x, when I process, I get 2. But when I look at g of x, which is 2 times the absolute value of x, my result is twice as large. Again, it's a vertical stretch, and I would say by a factor of 2. These are things we are going to be tested on. You have to be able to recognize this. Oh, by the way, if we look at this, we look at the slope. Up 2 over 1. Slope is 2. Again, here is the original function in red, but this time we have a vertical shrink of a half. So all my y values are half of what they were originally. So here's my original y value, it's half. Here's my original y value, it's half. Here's my original y value, it's half. My original y value is 1, I get half. My original y value is 2, I get 1. So this again is a vertical shrink by a factor of 1/2. All right? So those are vertical stretching and shrinking. And again, they make perfect sense. And by the way, if we look, the slope is 1/2. That might be important later. Horizontal stretching or shrinking of the graph of a function. So now it says, suppose that a is greater than 0. If a point x comma y lies on the graph of y equals f of x, then the point xa. So it affects the x value. The y values don't change, it's the x values that are getting changed. Lies on the graph of y is equal to f of a of x. All right, so this is what they're saying inside the function. It says, look, if 0 is less than a is less than 1, then the graph of y equals f of x is a horizontal stretch. Interesting. So if the a value is less than, it doesn't make it bigger like it did vertically. Remember I said this is Bizarro world. It's a stretch, right? Something between 0 and 1 was a shrink vertically. But in a horizontal world, it's Bizarro world. 1/2 doesn't doesn't shrink it, it stretches. It's Bizarro world. Does the opposite of what you would expect it to do. Again, if that was vertical and the number was between 0 and 1, I'd say, oh, it's a shrink. But it's horizontal. Bizarro world does the opposite of what we intuitively think, so it's a stretch, not a shrink. So when it's between 0 and 1 and it's a horizontal, it's a stretch. So now we're going to say if a is greater than 1, in the vertical world, that would have been a stretch. But in here, it's going to be a shrink. It says the graph of y is equal to fa of x is a vertical shrinking of the graph of y equals f of x. Again, Bizarro world. A is greater than 1. You would have thought it made it bigger, but no, it's going to be a shrink because it's inside the function. So let's look at some functions. Here's the base function. Y is equal to f of x. Then I process y is equal to fa of x. My a value is between 0 and 1, so it's smaller. It's a horizontal stretch. So this is that if I took the function and I grabbed it from the left and right and I pulled it, that's what it means. So let's look at this one. Here's the original function in black. Y equals f of x. And then in blue, y is equal to f a of x. But this time the a value is greater than 1. It's a horizontal shrinking, not a horizontal stretch. Okay? So remember, horizontal movements are the exact opposite of what you would intuitively think, Bizarro world, where vertical makes perfect sense. Let's look at vertical translations. Given a function g, defined by g of x is equal to f of x plus c, where c is a real number. It says for every point xy on the graph of f, there will be a corresponding point x, comma y plus c. So it affects the y values by adding whatever c is, and c could be a negative number, so we don't know what that is, so it could be adding or subtracting. All right, so what's neat about this is when we get to the point where we have to translate, I could start just looking at the x or the y values and start manipulating them based off the translation type. It says the graph of g will be the same as the graph of f, but translated c units up if c is positive, or the absolute value of c units down if c is negative. The graph of g is a vertical translation, so again, here is my parent graph, f of x equals the absolute value of x. If we want to look at g of x is equal to the absolute value of x subtract 4, then all my y values are down 4 units from where they were. Well, if this was 0, it's negative 4. This would have been 4, that's why it's 0. This one would have been 4, that's why it's negative, it's 0. So it's a translation of 4 units. It moves all the y values 4 lower. So I could subtract 4 from the y values. Here's just another example using a different function. Here's the base function, y equals x squared. Then I could take in red y equals x squared plus 2. So I'm going to add 2 to all my y values. Or I could look at this one and say it's y is equal to x squared minus 6. So I'm going to take all my y values and subtract 6 from them. And that's how I'm going to translate them. Again, vertical translations make perfect sense. I will add or subtract as needed for the vertical translations. Horizontal translations. Well, Here we go again. Horizontal translations, bizarro world. They're going to do the opposite of what I think. It says, given a function g defined by g of x is equal to the f of x subtract c, where c is a real number. It says for every point xy on the graph of f, there will be a corresponding point x plus that c value. So I'm going to add whatever c is, if it's c is positive or negative. Remember, it says x subtract c, that's important, right? X subtract c, I add c. So if it's x plus c, right? If it's f of x plus c, that's the same thing as saying f of x minus a minus c. So my point would be x plus a minus c when I'm dealing with adding or subtracting. Remember, bizarro world. The graph of g will be the same as the graph of f, but the translated c units to the right if c is positive, or the absolute value c units to the left if c is negative. The graph of g is a horizontal translation of the function. So my parent function, f of x, is equal to the absolute value of x here. This says x minus 4, so I'm going to add 4 units to x. So see, they're all moved over 4 units to the right. It's a shift to the right. Okay? Let's look at another example. My original graph, y equals x squared, right? Then I have this one here, which is x plus 2. Inside my function, it's x plus 2, so it would be y is equal to x minus a minus 2, quantity squared. So I'm going to add a negative 2 to all my y values, or move it to the left 2 units. All my x values, not my y values, all my x values. And then in here, this function, x minus 6. So I'm going to add 6 to all my x values, or translated 6 units to the right. Right? Translated 6 units to the right. 2 units to the left. All right. Here's another set. Here's the original function, y equals f of x. In red. This is y is equal to f of x plus 2. Again, x plus 2 is inside the function. X plus 2, that means subtract 2 from all my x values, or translate it 2 units to the left. In this function, y equals f of x minus 3. X minus 3, again, inside horizontal. X minus 3 says move to the right 3 units, so I'll add 3 units to all my x values. And that's how that's done. Here's the summary of all the translations. If I give you the function y equals f of x plus c, I'm going to move up, and I'm going to tell you c units. If I get y is equal to f of x minus c, I'm going to move down that many units c. If I get y is equal to f of x plus c, that means I'm going to move this to the left c units. And if it's f of x minus c, then I'm going to move to the right c units. So let's look at some examples. Graph the following, including the original graph. So f of x equals x squared would be the original. So here it is 2, 4, 2, 4. All right, if I wanted to look at a table, x, y, I'd say negative 2, negative 1, 0, 1, 2. I process those into the x squared, 4, 1, 0, 1, 4. So now let's look at the translation. F of x is equal to x squared plus 2. Well, we talked about this, and I'm not going to do the algebra right now. I'm going to cheat a little. I'm going to look at the same 2 points, because these are vertical, so I can look at the x values. And I was told before I can just add 2, right? because it's a vertical translation. The y values, I'm adding 2 to them. So what was 4 becomes 6. What was 1 becomes 3. 0 is 2. My y value was 1, 3. My y value is 4, 6. Now let's try this out. F of negative 2 is equal to negative 2 squared plus 2. Negative 2 squared is 4 plus 2, 6. So I was correct. So it's going to look like the same function, but everything's going to be raised up 2 units. I have a 0 here. Right, 2, 4, 6. So this is what the function looks like. Again, this is a sketch. You will have to do this on your test. All right. So understanding what's going on will make my life a lot more easy to do. Let's look at this problem. The parent function, again, is f of x is equal to x squared. Well, I'm just going to cheat a little. I'm going to copy all this. Change it to the same color. So those are the points. No sense graphing them again, right? And the graph looked like this: 0, 0, 1, 2, 4. All right. So now this is inside my function, right? This is inside my function. So it's a horizontal translation. X, y. That means I affect my x values, not my y values. So let's look at the same x values we had before. 4, 1, 0, not the x values, the y values. But now it says, according to this, it's in the form of x minus a minus 4, right? C is equal to negative 4. So I'm going to add negative 4 units to everything. So I had negative 2 subtract 4, or negative 6. So my new x value is negative 6, based off of this. Here I had negative 1. Negative 1 minus 4 equals negative 5. Negative 5. 0. 0 minus 4 equals negative 4. I had 1. 1 minus 4 is equal to negative 3. I had 2 minus 4, or negative 2. So all I did was play around with my x because it's a horizontal translation. It says move the graph to the left 4 units. So my new points are negative 4, 0. 1, 2, 3, 4. There it goes. Let me put that in red real quick. So all this I'm going to do in red. There's the point in red. Negative 6, 4. That's 4, 5, 6. 1, 2, 3, 4. Negative 5, 1. Negative 3, 1. Negative 2, 4. And it does look like I took the blue function. Right, it looks like I took this function, I just moved it over here. Moved it over that many units. Alright, so that's a horizontal translation. Again, bizarre world, going the opposite. So this is nice because I could check my work, right? I can put negative 6 in. I said f of negative 6. Well, that's negative 6 plus 4 squared. That's negative 2 squared, or 4. Yep, that's what I got. I can check them. But what happens if it's not a function I know? If I don't know the function, I have to find another way to do it. I must then move the points. I can't go back and test. So I have to be comfortable. Yes, on the test you will have a problem like this where I'm going to say, given this function, can you translate it? So what you need to do is find hard points. Right? This point here is negative 4, 0. This point here is 2, 2. That point 0, 0. This point is 1 comma negative 4, and that point's 3, 0. Those are the important points. This highlights my high point. I would only move points like this that were easy to detect, right? I would not worry about points along here, here, this part, or here, because I'm going to sketch it in. When I'm going to grade this, or when your professor or instructor grades this, they're going to do exactly what I'm telling you to do. They're going to grade it the way I'm grading it, the way I'm going to show you right now. They're only going to look at those 1, 2, 3, 4, 5 points because they're hard points. You only want points that are going to end, like if it was something like this, then it does something like this, and here, they're going to say move these points only. Don't worry about all the other points, all right? Move the hard points. So, let's look at this function here. This is a vertical translation down 2 units, which means change y by subtracting 2 from the original y. So let's look at our points. We have, and I'm going to just put them in this order, -4, 0, 2, 2, by the way it's -2, I don't know why I wrote 2, 0, 0, 1, -4, 3, 0. So those were the original points. They're going to go add 2 to y values. So my new points, my x values are not going to be affected, but I'm going to add 2 to my y values. So 0, when I add 2 to it, it becomes 2. Here's 2, when I add to it, it becomes 4. 0, that 0 when I add to it becomes 2. -4, when I add 2 to -4, I get -2. 0, when I add 2 to that, I get 2. So this is what the function should look like. Up top you see the original. Now I have -4, -2, and -4, +2, -4, +2, -2, +4, 2, 4, 0, 2, 1, -2, and then 3, +2. So if I sketch it by connecting the dots, that should look like the original function just raised up 2 units, and I would say that's close enough. Alright? When you're doing this, let's try not to make it harder than it has to be. Let's only move what we need to. So I would translate exactly how I'm doing this. So maybe you want to try this one. This is a horizontal translation, right? This is a horizontal translation. Right, it's 2 units to the right, correct, the right. We're going to add 2 to each x value. So again, we know our points. These are our points right here. We're going to add 2 only to the x, leaving the y values alone. So adding 2 to -4 makes it -2, sorry. -4 plus 2. All right, -2 when I add 2 to it is 0. When I take 0 and I add 2 to it, I get 2. When I take 1 and I add 2 to it, I get 3. When I have 3 and I add 2 to it, I get 5. And remember, I did not affect the y value, so it's -2, 0. It's no longer -2, 2, it's 0, 2. It's no longer 0, 0, it's 2, 0. It's no longer 1, -4, it's 3, -4. It's no longer 3, 0, it's 5, 0. So it should look like the original graph, except for it's been translated 2 units to the right. -2, 0, 0, 2, 2, 0, 3, -4, and 5, 0. So here it goes. Again, it looks just like the original function, except for it's translated 2 units to the right. And see, we're going to do more than one translation. So let's do them in the order I see them. This has a horizontal translation. By the way, the translations go in order of operations inside the function, then outside the function. All right. It has a horizontal here, +1. So that means to the left, 1 unit. Or subtract 1 from the x values. That's what this is. That's the horizontal translation. It also has a +2, which is a vertical translation. Up 2 units, which means I'm going to add 2 to my y values. So again, I have the same ordered pairs I had before. And they're going to get translated. So it says horizontal translation. I'm going to subtract 1 from my x values. All right. So -4, when I subtract 1 from it, gives me a -5. -2, subtract, right, so I have -2, subtract 1, -3. 0, subtract 1, -1. 1, subtract 1, 0. 3, subtract 1 is 2. So I just finished taking care of the horizontal translations. Now I'm going to take care of the vertical. And the vertical says add 2 to my y values. So I had 0. I'm going to add 2 to it. That becomes 2. I had 2 here. I'm going to add 2 to it. It becomes 4. I had 0. I add 2. It becomes 2. -4 when I add 2, right? -4 plus 2, -2. All right. And then I had 0. When I add 2 to it, I get 2. So now let's look what this function looks like. -5, 1, 2, 3, 4, 5, +2. -3, 1, 2, 3, +4, 2, 4. -1, +2. 0 is -2. And 2 is +2. So it should look like the original, but in this case, it should have been raised up 2 units and shifted over 1. So it's translated 1 unit over, right? There we go. And here's the last one. All it is a reflection, right? It's a reflection across the across the y-axis, sorry. What does that mean? Change the x to their opposites. So, given these original we're going to make the x's the opposite of what they were. So what was a -4 becomes a +4. I do not affect the y. -2, 2 becomes +2, 2. 0, 0, where there is no opposite of 0, it's just 0. 1, -4, my y value, which was my x value, which was a 1, becomes a -1. It does not affect the y value of -4. My 0.30, x was 3, becomes the opposite, -3, 0. So we're going to plot this 4, 0, that's my first point. 2, 2, 0, 0. I have -1, -4, 1, 2, 3, 4, and -3, 0, 1, 2, 3. And it should look like the opposite, like it retook this picture and I flipped it across the y-axis, right? So when I flipped it, it should do this. Right? That's what we did. So now we have it drawn. Right? That is reflecting. So here's a list of the summary of graphing techniques. It's very important. You will need this on the test. You need to memorize this. It says in the description that follows, assume that a is greater than 0, h is greater than 0, and k is greater than 0 in comparison with the graph of y equals f of x. It says the graph of y is equal to f of x is equal to y is equal to f of x plus k means I translated k units up. In other words, I added k to all my y values of the original function. The graph y is equal to f of x minus k is translated k units down, so I would have to subtract k units from every y value in the original function. The graph y is equal to f of x plus h is translated h units to the left, so I would subtract h from every x value to move it to the left. The graph of y is equal to f of x minus h is translated h units to the right, which means I would add h units to each x value. The graph of y is equal to a f of x is a vertical stretching of the graph of y equals f of x if a is greater than 1, which makes sense. If it is a vertical shrinking if a is between 0 and 1, again, making sense, it's vertical. The graph of y is equal to f of a of x is a horizontal stretching of the graph of y is equal to f of x if a is between 0 and 1. And again, bizarro world, a fraction between 0 and 1, you think it's going to make it bigger. I mean, you think it's going to make it smaller, but it's going to make it bigger. It's a bizarro world. If that a value is greater than 1, it's going to shrink it, where you want to think it's going to make it bigger because that makes sense, but it's bizarro world. So when a is greater, it shrinks. In number 7, it says the graph of y is equal to minus f of x is a reflection across the x-axis. And in 8, it says the graph of y is equal to f of the opposite of x is a reflection across the y-axis. And that's the problem we just did up here in D. This was D. All right. We are almost done. We have a few more things to do. Describe stretching and translations for the graph based on y equals x squared. You're going to have problems like this on your test, again, so you need to be able to understand this. We would prefer you to give it to us in the correct order, but I'm sure most of us will be happy if you just tell us what happened. So, orders of operations says start inside. Minus 7, that's horizontal. Minus 7. So that means I'm adding 7 units to the x values, right? So it's a horizontal shift to the right, 7 units. That's my answer. We also have this plus 2. That's a vertical 2 unit, which is adding 2 units to the y values. Which means it's up 2 units. That would be my answer. So those are my two. What are all the translations? A horizontal shift right 7 units. The other is vertical up 2 units. Or you could just say up 2 units, right? Vertical is kind of redundant. Let's look at the next problem. Inside, we'll start inside. It's horizontal plus 2. So opposite of what I want to think is plus 2 is adding, but it's not, right? It's horizontal, bizarre world. I go to the right, I'm gonna go to the left 2 units. Here's my first part of the translation. My next part tells me I have this 1/2. Well, that's on the outside, so that's a vertical. It's 1/2, so it's between 0 and 1, right? So it makes sense. It's vertical. Shrink. Vertical shrink. Factor 1/2. We're almost done this problem. What do we have left? We have this minus. Again, on the outside, the minus, remember that? It's across the x-axis. Reflect across x-axis. That makes sense because all the values are going to be the opposite of what they should have been. All my y values are now the opposite of what they would have been. That only happens when I reflect it across the x-axis, right? Because the x-axis is this one. This is the y, this is the x. So if this was the original, it's now over here, reflected across the x-axis. All right, look at this. This has a lot going on. 4, it's on the inside. That's horizontal. That's at a value. A is greater than 4. What does the opposite of what I want to take? It's not going to make it bigger. It's going to shrink. So horizontal shrink. Factor 4. Right? Bizarro world. Sorry, I'm just highlighting what I didn't highlight up here before. I have this, the negative. That's also horizontal. That's inside. And remember, that's this. Reflects across the y-axis. And I still have one more thing to take care of. I still have to take care of this minus 5. That's a vertical translation. It's subtracting, so it's down 5 units. All right. Now it says we want to find the points that are symmetric to the given points with respect to A, the x-axis, B, the y-axis, and C, the origin. A. With respect to the x-axis, that means my y values changed. So my x values stay the same, and my y values become the exact opposite. B says symmetric with respect to the y-axis. So that means my x values change, but my y values stay the same as the original one. And then in C, it says the origin, and remember that whole test was to replace x with the opposite of x, or y with the opposite of y's. Right? Going back all the way up here, it starts talking vertical translations. Where's the symmetry? Symmetry, even odds. Symmetry, it says, well, that's, right. It says replace x with minus x and y with minus y. Right? Symmetry with respect to the origin. Right? So here we go. It says replace x with the opposite of x, so it's minus 5. Negative 3 gets replaced with the opposite, 3. That is now respect to the origin. Alright. That's a 1, by the way. You're probably wondering what number that is. So I want you to take a moment and try these out yourself. Find A, B, and C. I would pause the video and try it. Alright, I assume you've tried it, and hopefully you have the same answers I have. First, we want to be respect to the x-axis. Well, if it's the x-axis, that means the y values change. Minus 6, minus 1. It was a positive one, so now it has to be a minus 1. With the y-axis, that means my x values have to become the opposites. So it was a minus 6, it now has to become a positive 6, and my y values do not change. To be symmetric with respect to the origin, my x and my y values must become the opposites. It was a negative 6, it becomes a positive 6. It was 1, it becomes a negative 1. All right, that's how we do that. Let me throw in one more problem to go over, and then we can stop. I want to write the equation for the function y equals f of x graphed below. So I'm going to look at that and I say, well, it looks like the absolute value of x. But it also looks like the absolute value of x. Sorry, I got to write this so you can understand what I wrote. Except for it's reflected across the x-axis, because absolute value of x, let me draw this out a little better for you. So it's there. The absolute value of x looks like this. Something very close to that. So if I look, it looks like it was reflected across the x-axis, which means it's a f of x like this. So my new function, f of x, is equal to the opposite of x. Opposite value. So I took care of that problem. What also looked like it went to the right. Right? It moved to the right. 5, 6, 7. Moved to the right 7. Right? Moved right 7. If I move to the right 7, that must mean I have to be minus x subtract 7, right? Bizarre world. It's not plus 7, it's minus 7. Because I have to subtract from there. So now we're almost there, right? I took care of reflecting, I moved to the right, but it also went up 1, 2, 3, 4, 5, 6, 7, 8 units. So my final answer has a vertical translation of 8 units up. This is my problem. Now, wait a second. It doesn't quite look the same, right? If I took that other function, it has a different slope. What is the slope here? Let's see. 1, 2, 3, 1. 3 over 1. Slope is either 3, it's plus or minus 3 depending on the side. So it must have a vertical stretch, right? Because it looks like it stretched this whole thing. So here is the answer. That is my final answer. I could test points. Let's test 2 points to make sure we're right. Let's see what happens at this point here. So it's 1, 2, 3, 4, 5. X is 5. So I get negative 3, 5 minus 7 plus 8. Negative 3, that's negative 2 plus 8. That's negative 6 plus 8, or 2. 1, 2. Yep, that's the right point. If we test this point, which is 7, 1, 2, 3, 4, 5, 6, 7, x equals 7, I get negative 3, 7 minus 7 plus 8, negative 3 is 0 plus 8, the absolute value of 0 is 0, negative 3 times 0 is 0 plus 8, 8. This is correct. That is my answer. Thank you very much. I hope you enjoyed this video, and I will talk to everybody later, and good luck with the rest of the semester.